All right, well, we need to finish what we were doing with improper integrals. We were saying at the end that if you had a region like this that had an infinity, go to infinity or minus infinity in the middle, or one on each side. At C, in the middle of an interval from A to B, this is equation 3, you could say that the integral from A to B of f of x dx, if it didn't have any other problems, is the limit as d approaches C from the left of the integral from A to B f of x. That's taking d here and then taking this area, taking d a little closer, and taking this area a little closer. And the limit of these areas as you get closer and closer to C, it's trying to calculate the area on the left. I think the picture helps you remember this more than the formula. Then you add to that the limit as d goes to C to the right of the integral from d to b f of x dx. So that'll be formula 3. That one's calculating the area under the curve from D to C, and then making D a little smaller, taking this area, making D a little smaller, taking this area. In the limit, it calculates this area on the right. And so you're taking this one on the left and this one on the right. And their sum is the value of the integral with an infinity in the middle. Now, what's more, we can do it if infinity is at an end. This kind of case where it goes from A to B, and there's an infinity at one end but not the other, and otherwise it's continuous. Y equals f of x. I should put that in the first one. So we can say the integral from A to B in this case is limit, just as d, if you like, goes to A to the right, of the integral from D to B f of x. So it's like this one just computing the right side, right? Or we can take, if the infinity is on the right end and there's no other problems, something like this. There's another asymptote. We can say that this integral from A to B, f of x dx, is the limit as d approaches b from the left of the integral from A to D, f of x dx. That's those. And then finally, one case we didn't consider before, suppose it goes from minus infinity to infinity. We did infinity on the right or minus infinity on the left. What if it goes from minus infinity to infinity, f of x dx, on a continuous function, no other things, problems in the middle? We'll say that this one has to be broken up into two parts. We think of it like this. You want the area under the curve from minus infinity to infinity. It doesn't matter where you break it. You take any point C, take the area on the left, plus the area on the right. What we want then is the integral from minus infinity to C of f of x dx, which we defined last time. That was formula 2, plus the integral from C to infinity, f of x dx. That was formula 2. Each of these was defined as a limit. And so now we have 6 different cases, and then you can make more than that, right? You can have one that has an infinity, multiple infinities in the middle. You got to make them. We can also break it up if it goes to infinity one side and an infinity in the middle. So you just have to break it up into multiple of these kind of integrals if there's some other problem in the midpoint. Let me do one off a limit. Now, one of the exercises with a sign that I think is pretty interesting. There's actually 2 of them. Maybe we can look at real quick. Suppose I had to take and evaluate the integral from 0 to 1 of natural log of 8x dx. How about that? That doesn't look like there's anything improper about it, does it? But here's what you do. ln of 8x, properties of algebra is ln 8 plus ln x. So I can graph that immediately. I just graph ln of x, which I know very well. And then ln 8 is just a number. So I can slide it vertically and make the same change. Here's y equals ln x plus 8, which is also ln of 8x. So it has an infinity at 0. What was the number we're calculating? Right? Remember, work, it estimates the area above the x-axis here and subtracts off the area below here. Negative numbers, that was less a greater area than this. Right? It's this area minus this area above minus below. So let's see, according to our procedure here, when infinity is on the left, we break this up and rewrite this as limit a goes to 0 from the right of the integral from a to 1 ln 8x dx. Now, how do you integrate ln 8x, right? Remember that one? It's testing your recent abilities. When you have a logarithm in here, often integration by parts. Let's try u for ln 8x and dv for dx. Then this is limit a goes to 0 from the right, and if u is ln 8x, du is the derivative of ln 8x, is 1 over 8x times 8 dx is just 1 over x dx. Isn't 1 over x the derivative of ln x? Of course it is. ln 8x is just a constant plus ln of x. It has the same derivative, right? It's 0 plus 1 over x. So they have the ln 8x and ln x have the same derivative. 1 over x dx for du. We'll take uv, which is ln 8x times what v. If dv is dx, then v is x. So uv is x ln 8x. And then it's minus integral v, which is x, du, which is 1 over x dx. We need to plug in a and 1 and then take the limit as a goes to 0 from the right. Well, what is this? This is limit a goes to 0 from the right of, put in the top end, 0.1 ln 8 minus, well, this one's it's just integral of 1, so it comes out to be x. It's minus 1. 1 ln 8 minus 1. When I put in the bottom end point a, I get a ln 8a minus x if I is a. There it is. So there's plugging in 1 and a and taking the difference. Well, what does this come out to be? As a goes to 0, these are constants, right? So this just becomes natural log of 8 minus 1. Comes out. What's the limit of this part? We have minus limit a goes to 0 from the right of a natural log 8a. And then plus limit as a goes to 0 of a is 0. This one goes to 0. This one's not so easy because this is going to 0, but this is going to infinity. Right? So it's a 0 times an minus infinity, actually. It's hard to tell what their product is approaching. So what we do is we say, well, this is natural log 8 minus 1 minus, let's write it this way, limit as a goes to 0 from the right of ln 8a over 1 over a. Why would I make it more complicated like that? Well, it's because when I have an indeterminate form, a 0 times plus or minus infinity, I rewrite it as a quotient to use L'Hopital's rule, right? Now I can say this is an infinite minus infinity over plus infinity case. The limit of the quotient is equal to the limit of the quotient of the derivatives, right? So this is limit a goes to 0 from the right of derivative 8a, as we call is 1 over a. ln of 8a is 1 over 8 is 1 over a. Derivative of 1 over a is minus 1 over a squared, and L'Hopital's rule says that's the same limit. This is ln 8 minus 1 minus limit a goes to 0 from the right of minus a that's easy. Limit minus a is 0. So evidently the answer is natural log of 8 minus 1 for this one. But still have to work at it. If you have any questions, you can call my office hours or whatever. I can't get into my office right now. You can send me a text. Playbacks. Finally, let's do one more. What if I had integral from 0 to 1 of 1 over the square root of x minus 1 dx. That looks kind of innocuous too, doesn't it? I wonder what that could be. If you think about what the graph of that looks like, you don't have to know exactly. It's just that this is a continuous function. This is a continuous function. Quotient of continuous functions is continuous wherever the denominator is not 0. The denominator is not 0 except at 1. So what happens is this has an infinity at 1 where you get 1 over 0 tends to infinity. But it's whatever it looks like. I don't need to know exactly. But at 0 and in between is continuous. So it's single stroke of the pen, but approaching infinity as x approaches 1. So we're looking at this kind of case. We rewrite this one as limit c goes to 1 from the left of integral from a to c, integral from 0 to c of 1 over square root x minus 1 dx. Then you have to remember, what tricks do we have for integrating 1 over square root x minus 1? Oh, yeah, substitution. Let u equal x minus 1. Du is then derivative of that. Dx is 1 dx. So this becomes du, and this becomes u. Now I have the limit as c goes to 1 from the left. The integral of 1 over square root u is u to the minus 1/2 du, but I have to change the endpoints now, right? When x equals 0, u is 0 minus 1 is minus 1. Let's see, 0. Oh, I put this wrong. Should have been 1 minus x. Huh, sorry about that. 1 minus x. 1 minus x. And now du is minus dx. There we go. So this is minus du here. And now I've got minus the limit. C goes to 1 from the left of, and minus that limit of the integral. And now when x equals 0, u is 1 minus 0 is 1. When x equals c, u is 1 minus c. We rewrite the limit like that and say, now this is minus the limit as c approaches 1 from the left of integral of x to the minus 1/2 is x to the 1/2 over 1/2, or 2 square root. Let's say integral of u to the minus 1/2 is u to the plus 1/2 over 1/2, or 2 square root u. And then I have to put in 1 and 1 minus c and take the difference. So I have minus the limit. C goes to 1 from the left. Sorry about that mess up there. Twice the square root of 1 minus c. And you put in the top endpoint. Minus twice the integral of 1. The square root of 1. There we go. Well, the c approaches 1. This approaches square root of 0. It goes to 0. So I've got minus 2. This just comes out to be 2. Apparently, this area under here is 2. Okay, I hope that helps. And come to my office hours if